a black hole is a mathematically simple object, but you put it in the real universe, and it does all sorts of crazy things. It breaks apart stars that come too close to it. That gas swirls around it in a hot plasma, and it slowly makes its way down to the black hole. But in the meantime, shines, because it's a hot gas, it shines some light. And that's the only time you can actually glimpse that light. Once it crosses that event horizon, remember, we're not supposed to be able to see it. So we had to build computational simulations that took into account how the gas moves, what does the black hole do, what happens to light once it's produced by that hot gas. Does it come to our telescopes, or does it make its way into the black hole and disappear forever from the observable universe? So these ended up being sets of really complicated equations that we needed computational power to solve. We worked on that, and we realized that traditional computing methods, this is now around 2010, were not going to get us to where we wanted to go. So our group at the University of Arizona started bringing GPUs, graphic processor units, into scientific computing. Now GPUs are at the heart of all the AI models that we are finding out about more and more. But this is 14, 15 years ago. It wasn't the norm. It was a new computing architecture, and we had to work on ways to adapt them to solve scientific problems instead of just being useful for video games, which is what they were designed for. So I'll show you a little video from those times. This is my former student and postdoctoral fellow in the group, C.K. Chan. What he's going to do here is run one of these complex computer simulations, 1 million paths of light, all at the same time. And he's going to run it on his computer on a single GPU and control the entire simulation with his hands through a leap motion device that you can see right at the lower, just under his wrist. You can see it in this video. So here's what it looks like. He is integrating the equations forward, so all those paths of light interact with the black hole at once. He can run it forward, he can run it backwards, he can zoom in, zoom out, he can change the orientation in real time, solving Einstein's equations for how light moves through this medium for 1 million particles. So this was a game changer. It took us from our early predictions and our early analysis tools to what we needed in order to understand what we're seeing in the black hole images. So we were able to map a black hole with its hot swirling gas around it to images that we would see on our computers, which is the upper right-hand part of the screen, where you're seeing a snapshot of this is what it would look like. Okay? So that was on a single GPU. That certainly wasn't enough, but when we showed the proof of principle that this was a fruitful way to go, we were able to get support from the National Science Foundation and build a cluster of GPUs. At the time, the only one in a research university in the entire world. And here's a picture of me from 2012, proud with my baby. And we then were able to start running very large-scale simulations that were a game changer. So, for example, I claimed that the millimeter wavelength of light, according to the early calculations in 2000, were the right place to look. Now we could actually produce graphics like this actual simulations like this that showed that as you change the wavelength of light, you go from seeing the cloud, the torus, all the way down to the horizon. And not only that, but if you had the time resolution, you could also see the gas moving around the black hole in our observations. We didn't stop there. We built an entire simulation library, asking tons of what-if questions. What if the black hole is bigger? What if it's smaller? What if it's spinning around its axis? What if it's not spinning? What if the magnetic field around it is structured? What if it's tangled? What if the gas is coming at a higher rate than what we think? What if it's coming at a lower rate? What if we're looking at it sideways versus face on? We asked so many what-if questions, thanks to this network of simulations that we were able to build, that we made galleries of those. These are all, each one is many, many days of computing time on superclusters that are asking these what-if questions, because that's the only way you can get at a quantitative answer to, is Einstein's theory right? Is it really producing a singularity? And is it going to show us some deviations once we get this image from the telescopes from what we expect to see? So these allowed us to build tools to measure the properties of the black holes. This is very simplistic, but we basically needed to know how much light we're going to see, what the diameter of that bright ring, which we lovingly call the donut, is going to be, and how that ties in with what we want to know about the black hole. So that bridge between the visible and the invisible, we were able to build those tools. Now I'm going to show you the results. I was lucky enough to share it on behalf of the collaboration, the first picture of the black hole at the center of the Milky Way in 2022 in Washington, D.C. And the press coverage and the response from the public was truly amazing. We were very, very grateful for that. But we were even more grateful for the memes. Our orange donut. I think we called it a donut way too many times. So, joking aside, this is our black hole. This is the black hole at the center of our own galaxy, the Milky Way.